So I will talk about small molecule diffusion and barriers. If you are interested in further reading about this, there is a chapter we've been writing in a book called Handbook of Environmental Degradation of Materials, where we focus on barrier packaging materials. And also in our book, Applied Polymer Science, there is a chapter on transport properties. Yes. So by starting, why are polymers permeable? Why are they not tight like metals or glass? Well, that's because they are, let's see if I can get the pointer here, by the way. So it's because that they are not tight materials. There is free space. If you compare to metals, you have essentially two ways of transport, normal diffusion, so to say. We have interstitial diffusion, where small molecules can actually circumvent. In this case, it could be carbon in iron or in steel. So you have interstitial diffusion, and you have vacancy or substitutional diffusion as an alternative way for atoms to move in metals. So there is a free space created next to the atom, and then it can move into that space. Candles or paraffin materials are almost 100% or perhaps 100% crystalline. So the crystalline phase is not permeable to small molecules. Helium or hydrogen can actually go through crystals if there are defects, but otherwise those are tight, and the candle has essentially only crystals. So that is a very tight material. And one can consider it as a low molecular weight polyethylene. But as we go into larger molecules to polymers, they are not able to arrange in 100% crystalline fashion. So there will be amorphous regions, and there you have free volume. So first of all, how does this permeation occur? Well, the permeability, the amount of substance passing through a certain area per time, is related to the diffusivity, how fast this foreign molecule can move, and how eager it is to go into the material. So we have the solubility. If you can keep one of those or both very low, the permeability will be low. So one can actually tackle diffusivity or solubility or both. And coming back to them, that they are not tight, they have a certain free volume. And that free volume is then open for foreign molecules to get into. And of course, the larger this foreign molecule it is, the less space it will find for creating its own place. In the free volume theory, the diffusivity is it's exponentially related to the amount of free volume in the material. And for polymers without strong interactions, without hydrogen bonding and so on, one can actually add the free volume from the polymer and the diffusing molecule. So the diffusing molecule has a free volume F1 here, and the polymer has a free volume F2. And you can actually add up these and get the total free volume in the system. And perhaps a little bit non-intuitively, you would expect that the small molecule will have a small free volume because it can pack densely, but that's not the case. You have the smaller molecules are actually coming in with a greater free volume. And that's the reason why you have that you often observe a diffusivity that increases with the concentration of water or some hydrocarbon and so on. So this plasticization or this increase in diffusivity due to plasticization is because this foreign molecule comes with an extra free volume to the system. To obtain the total free volume in water and polyvinyl alcohol, for example, then that's much more tricky. Then they are not really additive like this. But for a non-polar or hydrophobic polymer and a hydrophobic foreign molecule, it can be oxygen, it can be methane. So then you can actually add those up. And the fact that they are not tight, that there is free space, creates different kinds of problems also. I write a question here. What is the free volume of a PET material in a PET bottle? The molecules vibrate, so they take up some extra space because of the vibrations, and then you have the size of the atoms itself. But if you go down to 0 K, everything stands still. And this question then is, how much free space is it if the atoms are standing still? And I will not wait for an answer from you. I will just say it. And it's around 50%. So 50% free volume in PET at 0 Kelvin. And as when you increase temperature, the atoms are not expanding, but they will start to vibrate and take up space. So the fractional free volume or the free volume will decrease because of that. But that's good to have in mind that it's a lot of free space in polymers. And that has also practical implications. Here is a very old study that we did, which points to the issue with if you package different types of liquid food in a polymer package. Because they are not tight, they will actually absorb molecules. This is a study where we looked at fermented milk, or filmjölk in Swedish, contained in packages with a polyethylene inner layer, or a polyketone, as you see here. The interesting thing by looking at polyethylene and polyketone is that they are very different polarity, they behave very differently in terms of chemistry. You can see in the first column, here's the permeability of oxygen. It's very high for a low density or very low density polyethylene. With increasing crystallinity, the permeability goes down because the crystals are tight, as I mentioned. And if you add some polar group, like the keto groups here, you are also drastically reducing the oxygen permeability. Now, if you have this material and you have the fermented milk in it, you will actually observe things. And I don't remember now how long time we had it in contact with fermented milk. But you see, the fact that you have this liquid food inside, you are actually increasing the permeability. And for a low density one, it's quite drastically. For polyketone, it's much less, because what is happening is that the fat or the hydrophobic components of the milk is actually going into the packaging material and plasticize it. And there is very little, the hydrophobic substances don't want to go into a polar polymer like polyketone. And you can see the differences here. You also have effects on water, but that's a bit different things. But I think this thing with the oxygen permeability is quite pedagogic or illustrative, I should say, that when you have a packaging material, it's not, you cannot just rely on that you have a certain permeability or diffusivity. It depends on how the food stuff will interact with the material. I will show some slides on molecular dynamics simulations that we have done or others have done, because it is a very good tool for understanding how foreign molecules jump around in our structure. And you can actually observe different types of behavior in terms of how the molecules are jumping around. As you vary temperature, if you go from low temperature to high temperature, you will observe a change in the mechanisms of this hopping transport. If you go from low to high temperature, you will go from something referred to as a cage-like diffusion into something we can refer to as a liquid-like diffusion. And you can see the chart here is MD simulated jump length probability for quite a lot of calculations. It shows 3 temperatures. This is methane in polystyrene. And what is interesting is, well, the behavior, how it jumps. Here you have more discrete steps, so to say. In the liquid-like diffusion, you have less well-defined jumps, so to say. But what is interesting is that this transition occurs way above the glass transition. So it's not directly correlated to the glass transition. It's actually quite far from it where we see this, where one has seen this difference. So the cage-like is, you can consider the foreign molecule to move around, not to move around, but to vibrate like this in a cage. And eventually it makes a jump into another cage and vibrates. This is a very exaggerated image because you can see here on the jump length here that we're talking very small jumps, actually. And in the liquid-like type, there's more like the foreign molecule is moving with the polymer molecules. This is showing a bit the same thing. Now, this is glycerol diffusion in starch. And you can compare, this is jump maps, or actually it's the distance that the molecule has traveled as a function of time. Though these curves are useful to calculate diffusivities, for example. If you have glycerol in glycerol, you have more or less a straight line. And here you have a pure liquid-like diffusion. You don't have this jumping around. Vibration and then jumping and vibration. Now, if you put glycerol not among itself, but into a rather rigid polymer, these square displacement curves are looking different. You don't have a straight line from the beginning. You have a non-linear curve, and at longer times, when you track it, it becomes linear. This is 2 cases where you have, this is without 3% water in it, and this is with water. So you see the effect of water, how it does it. And you can fit these curves with, so MSD is the mean square displacement. It's what you have on the y-axis here. According to Einstein's theory, the slope of this curve should be proportional to the diffusivity of glycerol in glycerol in this upper case. However, when you have the glycerol in a polymer matrix, you will have this nonlinearity. So you had to add a term here, which considers this cage-like effect. And the second term here is the Einstein type of diffusion or random diffusion, and that is what you obtain at longer times. It's a straight line further on. So these are actually depending on how you look at the system. If you're interested in short times or long times, you will have different results. And A here is actually related to the box that the molecule moves. And again, it's a bit exaggerating calling it a box, because the length, if you fit the data, the length of this box is just 1 ångström, and clearly you won't fit a glycerol molecule in that. It nevertheless it can explain the observation one observes. So, and then you have a diffusivity for this cage-like motion, and you have a diffusivity for the random type of motion. And here's I put in a table here with this is a system with starch and 10% glycerol, and you can see that the diffusivity in the cage is much higher than the overall random diffusion. What is also interesting here is that with MD you can actually look at the diffusivity as a function of plasticizer content, as you can see in this graph here. So this is the same system. And what is very interesting is that there is a change in the curve between 20 and 30% glycerol. If you look in literature on bio-based polymers that are plasticized with different compounds, most works have been done at 20 or 30% plasticizer. So it's not a coincidence that it starts to work well in this region between 20 and 30%. And the reason that the plasticization starts to work, the increase leading to an increase in diffusivity here, is that one gets some type of percolation in the material of the foreign molecule of the plasticizer. So if you obtain a percolated structure here, the red ones here is glycerol molecules, you will see a change in the diffusivity, and that correlates directly to the mechanical properties also. I mean, if you have a higher mobility, you will also have a lower modulus and perhaps a more extensible materials. Here is an old study that we have done on a system where we put limonene in polyethylene. This is of practical interest because limonene is one of the flavor compounds in orange juice. And there are occasions where this limonene diffuses into the packaging to the extent that the taste of the juice gets bitter. So we have been looking at this system. Again, these are old. This is from 2002, I think. So what we do is we put the foreign molecule, limonene in this case, in the box, and then we shrink the system. And as you see here, we have to keep it rather small because you see if you go from a 25 angstrom box, that's doable, 850 atoms. If we go to 260 or 1 micron, you see how many atoms we need and therefore how slow the system will be. I mean, it will be, we have to run for long times. And talking about long times, this is the trajectory of the limonene molecule as a function of time. And we did the work up to 100 nanoseconds. In 2002, we did it on a PC, and it took essentially 1 year of real time to obtain these plots. So 1 year. And here you see on the right a jump map, and this jump map tells us that the system is, the foreign molecule is doing a liquid-like diffusion. And I can see it here. So we don't have a bump. We don't have this cage-like effect here. We have a straight line, essentially. And the measurements or the simulations were done at high temperature, as you see here. So it's not a surprise that it behaves more like a liquid-like motion at that temperature. I will skip that, and I will go into, now I will go into first the effects of the molecule size on the diffusivity, and then after that I will discuss or show things about the solubility. So can we predict the diffusivity based on the size of this foreign molecule that travels around in our polymer? One can do that. You see a plot here where you have the logarithm of the diffusivity as a function of molecular diameter. And it works well if the molecules are more or less spherical, or at least not very extended. And you see it's a straight line here, essentially. However, when you have long molecules, it's more difficult to tackle it, because you don't really know exactly how a long molecule moves. You could actually plot the data for a long molecule, considering the length of it and the diameter as one type of parameter. So here is another question. Guess the molecule, just to see how different it can be depending on the size of the molecule and the shape. So here we have 3 linear paraffins with different length, and we have cyclohexane, and we have 2,2-dimethylbutane. And then we have diffusivity as a function of the size of the molecule. This is in a polyethylene material. The ones that are fitted in a straight line here is actually these 3. And cyclohexane is there, and 2,2-dimethylbutane is here. And you can see here it's a log scale, so that the shape of the molecule has a very big impact, of course. It also tells you that these long molecules are diffusing in a similar way, probably with the long axis in the same direction on average with time. There are, apart from that, polymers are open structures or low density materials. There's also a lot of things that can happen in the polymer which leads to complex behavior. The curve, the chart I have to the upper left is referred to as a sorption isotherm. And it's essentially the concentration of the foreign molecule as a function of its vapor pressure or concentration around the material. And the simplest case, you have a straight line. This is referred to as Henry's law. So things are linear here, and you actually don't change the properties of the polymer. However, when you go to larger vapor pressures, there will be high concentrations of the foreign molecule, and you will see nonlinear effects. And here you have plasticization. For stiff polymers, you usually have this type of behavior. It's a Langmuir type initial uptake, and then you go at high concentrations, you also have this plasticization on top. And this Langmuir type of uptake has been modeled and explained by that there are microvoids in the material that this foreign molecule is filling. And when those voids are filled, you have a normal solution or dissolution process. The problem is that no one has seen these microvoids, but it's a good theory for comparisons, for example. If you have a high uptake, if you put your sample, immerse it in a liquid, and you measure the uptake as a function of time, very easy experiment. However, if your molecules, if the uptake is sizable, then you will see things happening to the material. You will have a one-dimensional swelling in the beginning because the middle part is not swelling and restricts a expansion in the perpendicular direction. When the foreign molecule reaches the middle, it is free to expand in all directions, and then it actually shrinks in the thickness direction. These things gives you a non-linear curve or uptake of mass uptake as a function of square root of time. So when you see these S shapes, it's most often due to this effect. And another thing that I have to point out here, because it's used a lot in actually not a correct way. When you calculate the permeability of water in polyvinyl alcohol, for example, you are calculating it based on that there is a linear concentration gradient between the high concentration side and the low concentration side. That allows you to relatively easily calculate the permeability. However, when you have these plasticizing systems, it's not a linear linear slope that drives the diffusion. It's actually can take extreme forms, very different from this linear one. So when you define or calculate the permeability of water in a system where water plasticizes it, you should not use the permeability P. You can call it specific water vapor transmission rate, for example. Other things that happens is if you have polar foreign molecules coming into your polar polymer or non-polar polymer, is that you can see clustering. And also, this is actually also a bit non-intuitive. And the clustering, and you observe this from sorption isotherm. You model the sorption isotherms with for example, a GAB model. With this model, you can actually determine the cluster size, which goes from 1 to almost 2.5 here. So this clustering leads to that the diffusivity, in this case, is water diffusing in proteins. You will actually see diffusivity that is increasing with concentration. You have plasticization, but you also have an opposite effect, a clustering effect. So if you plot the diffusivity versus the uptake of, for example, water, you will have this plasticization effect, but at higher contents of water, the clustering will dominate. So the diffusivity will go down. As you can see, if you plot the versus activity here, concentration of water, you see it goes up, the diffusivity, and then it goes down. And it's because water does not travel by itself. It travels together with a friend or several friends, and that makes a bigger molecule. So it diffuses slower in that case. Other cases of complex cases, I should say, are well, Fickian case. It's the normal uptake. You have mass uptake on the y-axis and square root of time on the x-axis. That would give you a linear slope if the system is referred to as Fickian. In case 2, this exponent will give you, it will take the value of 1 instead of 0.5. And case 2 is when there is most often a phase transition along with the diffusion. So if you are working with alcohols in PMMA or acetone in polystyrene, you will have like a front that is moving into the material. And the rate of this movement is determined to a large degree on the rate of the phase transition. You go from a glassy material to a plasticized rubbery material. I'll skip that. Now I can show you this. So now we go from diffusivity to solubility. And it's relatively easy to predict diffusivity if you compare to solubility, because in solubility there is a lot of things that can affect the uptake, the actual uptake. And it is difficult to predict, but there are ways to do it. And for example, using lattice fluids models. As we have done here. And what you need, without going deep into the theory, what you need is a PVT diagram, as you see here, for the polymer, and the PVT diagram for example, methane or nitrogen. With those data, you can actually predict not just the trend, but also the absolute uptake values, as you can see here, for these two species in polycarbonate, so nitrogen and methane. So there are ways actually not just to see trends, but also to see the absolute uptake. I will skip this part actually and go into barriers, how to create barrier materials. So this is, I put in the different strategies one can use for obtaining a high barrier. And I will go through this part by part. I will first look at or talk about polarity and also hydrogen bonding. We know from work from, for example, Lars Berglund's group that hydrogen bonding is not of extreme importance for the actual mechanical properties in polysaccharides or cellulose-based materials, but hydrogen bonding has an enormous effect on the diffusivity of foreign molecules. And what you see here are molecules that belong to those that are most tight, amorphous materials that are the most tight. And you have a combination of hydroxyl groups and also rigid groups. So these substances I show here, or these polymers I show here, have very low oxygen permeability. This table also shows you the effect of polarity, and it's actually interesting to compare polyvinyl alcohol to polyethylene here, because the only difference between these, they have similar crystallinity. The only difference is that you have the hydroxyl group in the repeating unit. And you can see the effect it has on the oxygen permeability. You go from 1, 2, 3, 4, 5, 6, 7, is it 7 magnitudes? Essentially. Now that's natural rubber. So yeah, six magnitudes in permeability between these two cases, which shows the extreme effect of hydrogen bonding. And you can also see that for other bio-based materials, when you have polar materials, you have hydrogen bonding in these cases, and those are very effective in stopping the molecule, for example, the oxygen molecule. However, as you see here, when water is around and you are actually destroying the hydrogen bonding between the polymer chains, you see the enormous effect it has on the permeability here. I will skip this because they show the jump chart and go to crystallinity. So this is a plot of polyethylenes with different crystallinity, and you see the effect of the density when you go from essentially amorphous, fully amorphous material to a high density polyethylene or medium density here. You see the effect it has on the water vapor transmission rate. And the reason is quite simple. You have crystals which are impermeable. They will block the water for moving around, delay the diffusion. Polyvinyl dichloride is a very common material in packaging, and it's because it's a quite tight material, which in turn is due to that it's highly crystalline. It also has some polarity, a little polarity, I should say, because you have these chlorines going on, sitting symmetric. Yeah, I said it's obvious there's there are crystals in the system. But however, it's not a two-phase system. As you can see in the lower left part here, I sketch crystal amorphous crystals, so a typical lamellar structure. But if you go closer and look, you actually have the crystals and you have the amorphous material, but you also have a crystal surface, which have a less order than the crystal, but more order than the amorphous, fully amorphous phase. And this crystal surface is also tighter bound to the crystal, so the mobility of the parts of the chains here are lower than the mobility of the amorphous component. You can model this by considering two effects then. Tortuosity means that the crystals are there and you have to circumvent. You have to circumvent the crystals, the diffusing molecule. So that's the labyrinth effect or the geometrical effect. But then you also have the constraint effect, beta here. You see how both of these reduce the diffusivity. And the constraints comes from the fact that the mobility in the full, if you consider the full non-crystalline layer here, the mobility on average is much less than for a pure amorphous polymer. So the constraints can be quite significant. We couldn't obtain a fully crystalline material polymer, but we can obtain an essentially fully crystalline liquid crystal polymer. And the advantage of that then to come up to very high degree of order or liquid crystalline order is that the diffusivity as well as the solubility goes down. The typical liquid crystalline polymers are forming domains like uncooked spaghetti, I can think about. But the borders between these phases, you have a less packed system or default. So it's here where the oxygen molecules, for example, can go through. And if you plot the water vapor permeability, observe it's a log scale versus the oxygen permeability, also log scale. You have the liquid crystalline polymers down here. So they are the best choice one can have in terms of both water vapor and oxygen barrier properties. I will skip those. I will go into chain stiffness. That's also a strategy to increase the barrier properties. A good example is a comparison between PET and polyethylene naphthalate, where you have this group instead of that group. The factor is an improvement of 3 in terms of oxygen barrier when you go from this structure to this structure. And PEN has also been used in packaging. I think still that the transparent Heinz ketchup bottle is produced by PEN, with PEN, to have a transparent material, but also to have a sufficient oxygen barrier, because the ketchups today don't contain any antioxidants in general, I think. The effect of putting a norbornene unit on a polymer or on a polyethylene chain is also enormous. You go from a glass transition about -70 to +80 by incorporating norbornene units. And this material you can find actually in blister packaging, if it's not PVDC. This is a slide I put in. I will continue a little bit more, Linda. I'm aware of the time. This is just we have done a work where we have done glycoproteins, so materials that contain both a polysaccharide, in this case arabinosilin, together with a protein, in this case gluten. And we've done oxygen permeability of the pure arabinosilin and the one with 50% gluten. And here you have the oxygen permeability, and this is the water vapor transmission rate. The specific one, I don't want to put permeability here, P, because it's not working, it's not correct. And you can see that with the inclusion of the protein, the permeability goes, or transmission rate goes up. So it's interesting to see that this type of structure is actually more effective in stopping, for example, oxygen than the protein structure. The protein has this peptide bond, which is taking actually behaves like as a double bond. So this unit is very stiff, but the carbon sitting next to it is very flexible. But you also have this big side groups that would reduce the mobility. But nevertheless, it seems that the polysaccharide beat the protein here. We have done work on furan-based polymers, and the interesting thing is that they are, this is essentially poly-PET, but with the aromatic ring we replaced by furan ring. What is the effect of that? Well, these polymers with the furan group has actually quite significantly better oxygen barrier properties than PET, as you can see here. We don't know if it's the diffusivity or the solubility or both that is causing this, but it's interesting to see that one can have a quite large effect by replacing the aromatic ring with the furan ring. Another strategy to obtain to obtain a barrier material is to close pack the molecules, not to the extent that they crystallize, but that they are laying very close to each other. And the very classic example of that is butyl rubber. Butyl rubber is essentially the only rubber that has barrier properties, and we should be happy about that, because that's the inner lining in bikes and cars and the tires. If we had natural rubber instead, we would probably need to fill it up with air maybe every second day or every third day, but we don't need to, and that's thanks to this molecule. So here the molecules are laying very close to each other, and there is a lot of friction when you try to move the chains, and that's why it gets warm if you use it as a squash ball, because butyl rubber is the squash ball. When the butyl rubber becomes warm because of the friction, the polymer chains gets further away from each other, and the material behaves flexible. You know, a butyl rubber ball does not bounce if it's not heated. Chemical crosslinks are also another alternative to obtain a better barrier. Here is a polyethylene that has been gamma ray treated, which yields carbon-carbon double bonds. And you can see the effects. This is the permeability, and this is the change in permeability between an unirradiated and one which is gamma radiated. And you can see that the diffusivity goes down with the gamma ray treatment, but the effect is most obvious or biggest the larger this penetrating molecule is, because a larger molecule needs more space, and therefore this cross-linking affects the larger molecule more. I'll skip that one. Fillers is also a way of obtaining a better barrier material. You can, for example, mix two polymers where one is much tighter than the others. Here is a liquid crystalline polymer polyethylene blend, and you can see that the diffusivity goes down with the content of the LCP, liquid crystal polymer, simply because the LCP phase in this case forms sheets also in the structure. A bit similar to if you have a clay composite, which is the data here, nano clay. You can produce blends. This is a blend of PET and PEN, and by blending these, you can actually steer the mobility and the glass transition. Here is oxygen permeability on the y-axis as a function of this monomer. This polymer in polyamide 6. So this is obviously a more steric or more stiff unit than polyamide 6, the polyamide 6 chain. So blending here reduces the permeability. Skip that. Further, chain orientation is also another way to obtain a higher barrier material. It's because you are actually forcing the molecules closer together, and you can also induce further crystallinity when you stretch it. Here's an example of methylene chloride diffusing in polyethylene or polypropylene. A is polyethylene, B is polypropylene, and this is the degree of stretching, so the stretch ratio or the elongation ratio. And you can see that there is a quite specific change at around a draw ratio of 8. And that's where you have the big change from a spherolytic to a non-spherolytic structure. You're starting to obtain fiber-like structures at around 8. It's quite a strong, large draw ratio here. Here is another study where we looked at polyketone and different draw ratios of polyketone. And we have oxygen, and we have carbon dioxide and water. And we can also see here a transition, which is more apparent for CO2 and also let's see, oxygen when it's dry. And this is also related to a quite strong change in the structure. Go from a spherolytic one to more fibrous one, or fibrous one. Here at the draw ratio of around 5. And these biaxially oriented systems are used a lot in packaging, not polyketone, but polypropylene. Examples are these packagings here, because you are actually reducing the permeability of oxygen by this. External shielding or lamination is another method, or the final one I will mention, and it is when you look at a packaging, you will think that it's only one layer, but in almost all cases there are multi-layers. And here you have an example of a multi-layer, the mustard package here, which contains low-density polyethylene on the inside, so you can weld the material, you can weld the packaging, and then you have PET, and the PET is not a sufficient oxygen barrier, so you're actually putting aluminum, it's aluminum-coated PET. And then you have a lacquer on the outside, or actually then you have an imprint, and then you have a lacquer to keep to not destroy what's been printed. It's a fairly complex structure for basic packagings. Finally, I will just say something about this, because it's something we work on right now. We are looking at ways of so we are mimicking nature to obtain barrier solutions and bio-based barrier solutions at the end. And we have been looking at, for example, there are apples that keep the moisture for over a year. There are those that do not, of course. But as you see on the top here, I think this is 4 months after I bought the apple, I think. But there are apple sorts that can keep the water inside for a very long time. And then it's interesting to see how nature is solving that. Nature is solving that, and it looks a bit the same in other peels or other cuticles. You have on top a hydrophobic layer, a wax layer, and underneath you have a cross-linked polyester. Of course, this upper layer, the wax layer, is hindering water from getting out. It's a bit interesting also that this layer is not in contact with the high moist condition, but it's on the outside. I mean, it would probably be better to have it on the inside here. Nevertheless, this is how natures have solved it. And we mimic the coke polyester, or this cross-linked polyester, by using different hydroxy fatty acids or diacids. And so it's a project where we try to mimic nature and obtain good materials, good barrier materials, packaging materials. I think I will finish with that actually, and just say that for further reading is available here. Yes, Linda, I think we can.
Yes.
Sorry for taking 10 minutes more.
No problem. I don't know why. No. So maybe if we have any immediate questions, short ones, we can, if there's anything before the breakout session,
Yes.
we can allow for that. Do we have any immediate questions for Mikael?
I have one. Deniz, I am from Rice.
Yes.
Yeah, thank you for very nice presentation. I remember physical chemistry courses, what happens to 0 Kelvin? We were saying that electrons fall on nucleus. I'm not very sure if I understood well. What happens to free volume?
With temperature, for example.
Yeah, when we consider the polymers, are they just freezing or?
Yeah, I mean, the reason I put 0 K there is that the atoms are standing still. So then you see the non-atom space, so to say. But as temperature increases, the atoms are vibrating and they take up more free volume. Yeah, they are. That leads to lower free volume. So to go further, there is static free volume and dynamic free volume. So when it comes to diffusion, one is more interested in one is more interested in the dynamic free volume. And why I say dynamic is because it's not just that there's open space, but it's also the dynamics around the open space which is caused by the atoms or the polymer chains and so on. So and if you can actually determine the free volume from a diffusion measurement, but that free volume is then a dynamic free volume because it considers we obtain the free volume from a diffusing molecule. If you determine the free volume from a density measurement, for example, that's a static free volume, and those can be quite different. Actually, because if you have a more flexible polymer, your dynamic free volume will be higher than if you have a more stiff polymer. So there's actually different types of free volumes, but if you consider room temperature and a dynamic free volume, let's say that you have measured diffusion of oxygen in, let's say polyvinyl alcohol or something. And from that diffusivity, you obtain backwards a free volume through this exponential relation. Then that typically is like maybe 6%, 5% free volume. So it's much less than the static one and in particular to the one at 0 Kelvin. So that was a very long answer, but it is complex and the free volume you obtain depends on how you obtained it, so to say. But the free volume increases, the dynamic free volume increases, for example, over a glass transition as compared to below the glass transition. So you have actually a free volume that is increasing with temperature when you obtain it through for example, dynamic processes.
Okay, thank you very much. I actually have one more quick question, Linda. Am I allowed to?
Yeah, go ahead.
So you talked about when we add plasticizer, the actual reason is when they become or when they start percolation. So how likely is percolation when we use clay?
When you use?
When we add clay.
Yeah, but that is so that's the opposite then. You get the best properties if you have a percolated path of clay particles. Well, you get the best properties if you have them exfoliated in the system. But the more clay you put in, of course, there will be, at some stage, there will be like a percolated barrier over it, so to say. But the plasticization here is like, there's always between 20 and 30% by weight seems to be the region where you obtain plasticization in most systems. I mean, if you have 5% plasticizer, you don't have a plasticized system. If you have, yeah, so there is a transition, and we can see that both from simulations and experiment that there is a transition, and you can calculate the percolation concentration, and that depends on how the molecule looks like, because you will have a percolated plasticizer if you have a long molecule than a short one, but it's essentially when the big effects comes when you start to have continuous path of your plasticizer in the system, and you need to go. If you have round particles, the theoretical percolation concentration is around 27% or 20, somewhere there. So you need to go over that to have an effectively plasticized system.
Okay, thank you.
Thanks.
Thank you. So I will just stop